Hi, I'm Gene Chen, Yokogawa Stardom Product Manager. In this session, I'm going to review the Stardom Liquid Library API MPM Liquid Oil Correction Factors. This standard is based on the API MPM Standards Chapter 11.1. Temperature and pressure volume correction factors for generalized crude oils, refined products, and lubricating oils. In the last session, we reviewed 11.1.6.1. And in this session, we're going to review 11.1.6.2, which covers the method to correct volume and density from observed conditions to customary base conditions. And you may recall that the customary base conditions are at 60 degrees Fahrenheit at 1 atmosphere. Just as we did in the demonstration of 11.1.6.1, I'm using an Excel spreadsheet that acts as an OPC client to Stardom's OPC server. So the Excel spreadsheet takes in data under the entry area, sends it via OPC to the controller, where it's read back and to populate the test case results area. So there's an input part and an output part. The input matches the inputs put in on the test cases, and then the output should match the published API MPM results. So if I scroll over, there are 16 test cases for algorithm 11.1.6.2. If I scroll down to the first test case scenario and take a look at that, we can compare this against the API MPM published example. So if I go down to the published example 1 here, I can go ahead and take a look and show you that the inputs match up. So it's for generalized crude oil, which is commodity group 1. So we can look at CG is 1. Whoops. And sorry, CG is 1, and then the pressure is -5, so the pressure is -5, and then we have a density of 823.7, and this is the density of the oil at observed conditions, and then we have the volume at observed conditions as being 1,000 units, and it really doesn't matter if that's liters, gallons, barrels, it's any valid volume units. And so you can see here it says custom entry. That means that was from the custom entry, free entry area. But if we want to use the data from example 1, I have to click on the data 1 button or example 1 button. And now this data gets transferred over to the controller, read back, and put into the test case area. And just to show you that it is going to the controller, I can bring up the engineering environment here. And you can see that the inputs to this controller match up with the test case. So it's commodity group 1. It uses a observed temperature of 80.3 degrees Fahrenheit. This is 80.3. It's -5 degrees is the observed pressure. That's what we have here. And then we have the input density is 823.7 and observed volume is 1,000. So those all match up. And I'm not going to go through all these with one by one to match it up against the published API document. I just wanted to do that initially to show you that they did indeed match, and you can do that for yourselves to convince yourselves that this is true. For the remainder of the video, I'm going to go ahead and just leave up the engineering environment. This shows the function block in the Stardom engineering environment, and so I want you to be able to see that these inputs and outputs actually change as we go through the test cases. So you can see that the data really is going out to the controller and being read back into the Excel spreadsheet. So for test case 1, we can see that the results do match up identically, up to at least 8 decimal places, and in many cases, like this one here, the raw correction factor matches up, I think, to like 10 or 11 decimal places. Let's go ahead and count it. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places we match up to. So in all cases, we match to at least 8 decimal places. In many cases, we go full to 10 or 12 decimal places. We have a very high degree of precision, and only 8 decimal places are required in order to comply with the standard. So if I move on to the next test scenario, example 2, I can go ahead and click on that. You can see that the input values change on the function block, and then the calculated values are also reflected and they match identically. Now we can move on to the next test case, example 3. And there's a little trick here. These correction factor due to temperature, the correction factor due to pressure, and the combined temperature pressure correction factor. Those we know will be correct if the final values match. The final value that we're trying to correct is volume and density. So shortcut here, you can always look at them one by one, but I'm going to try to speed this up in this video just by having you kind of direct your attention to look at the density at 60 degrees, density at base conditions, which is 60 degrees Fahrenheit, and then volume at base conditions, which is 60 degrees Fahrenheit. You can see if that matches, if these two match the published results, then we know that the correction factors are correct. Otherwise, there's no way we could get that result, right? Okay, so you see that they do match in this case, and we can go ahead and quickly go into test case 4. Again, we see that the values over here changed. You can pause the video and match every line result to see that they do indeed match up. But just to make this go a little faster, I'm just trying to highlight the density at 60 degrees Fahrenheit, base conditions. They match, and then the volume at base conditions also matches. Again, these values are generated by inputting the observed density and inputting the observed volume and then correcting that to base conditions. So you can see here the observed density was 803.141 kilograms per cubic centimeters. The volume was 9,998.7, and then when you correct those to base conditions, this is the result here, 787.5. Whoops, I just moved the cursor over. 787.507922, they match up. And then on the volume also, it's 10,197.174, and they match up identically all the way out to up to 8 decimal places. So if I go to the next example, test case 6, you can see the controller inputs changed. New values were calculated for the densities and the volume. And that's also reflected over in the Excel spreadsheet. They all match up now. So once again, I'll pick out density at 60 degrees base. It matches identically with the published results in the API MPM standard. Same thing with the density. We have the 949.54, and that matches identically. So we go down to test case 7, and you can see that, again, I'm showing you should be able to see the screen change. You'll see that flicker at the corner of your eye, and you can then match up all the way across the board. All right, so they all match up. So you can see we have a very high degree of precision here, and you don't have to just use the test cases that are published in the API standards. If you have your own test cases that you've developed based on your history and experience with the variety of crudes that you're dealing with, you can enter those values into this spreadsheet as well, and you can do a test. You just call me up. We can do a WebEx session. I'll allow you to do free entry of the values and let the controller calculate the values and see if they match up for you. So once again, density at base 60, the calculated value matches the published value. The white is the published value, this gray area is the calculated value. Again, this is the calculated value, this is the published value in the standard. And here's I think this might be the last example. I think after this, then the API standard has the rest of the examples kind of test the limits. It wants to see that the algorithm throws an error and a status code to just tell you that it's reached its limits. After this example, I believe that's the case. You can see again, though, that these match up identically. So here we are, example 10. You can see that this is a limit. If I go ahead and I'll blow up the Excel sheet now, make it a little larger, you can see the rest of these test cases really deal with hitting the high or low limit for pressure, temperature, density, or all three. And it takes a little time when it hits all three of the limits. What I do to verify that I'm seeing all three of the limits, I'll go ahead and, for example, on test case 11, I'll change. We'll go ahead and run test case 11 first. You can see that I got a true result. It says example 11, and that's correct. The result throws a status code of 1, which says the temperature is out of range. So it says here, temperature input out of range, and that's what the published standard was checking for. It says the temperature is greater than 302 degrees. So if we drop this down to 302 exactly, then we can see if then it catches the error and run the test again, we can see if it catches the pressure condition. And it does. It generated a true result as an error, and now you can see the status code changed to a 2. And if we go check what the status code means, you can see 2 is pressure input out of range. So that's how you can kind of keep going through the whole test case to make sure all the ranges are checked all the way to the end. And so I've done that for all the test cases. And again, if you want to try out your own observed conditions, observed volume and density, and calculate what that volume and density would be at 60 degrees base conditions, so you can do that with this free entry box where it says custom entry. Okay, so that concludes this test or this demonstration. I'm going to go ahead in the next set of series of videos go ahead and cover the other equations of 11.1.6.3, 7.1, 7.2, and 7.3. So join me next time to review the rest of those.